right, sorry, running about 15 seconds late by my watch. All right, so my name is Dino Zovi. I'm the CTO and one of the co-founders of a company called Trail of Bits. I've spoken several times at Source before, and a few other places that you might have heard about. What I'll be talking about today is some Ios jailbreaks. One of the things that we try and do at Trail of Bits is take a different kind of analytical view at a lot of problems in information security and try and what we call think about it the right way. And so we focus on analyzing attacks in the wild, adversary capabilities, and just sort of and like their behavior and like their actions. Because one of the things that we're trying to do is a lot of times in security we're talking about this massive universe of possible attacks. And if you're trying to defend an organization, you can't defend against every possible attack that someone can dream up, or every possible attack that someone like me sitting in there working all day in their parents' basement can cook up. Luckily, attackers need to scale as well. So when you're defending your organization, the attacks that you're going to see are going to be repetitions of other attacks, and we use kind of this data to extrapolate from the actual attacks that are happening now to the what will be the probable attacks. And so this presentation is kind of taking some of that mindset and analysis methodology to the development of Ios jailbreaks, and I'll explain why we're doing that. So Ios jailbreaks and malicious attacks share a lot of the same technology. So what I refer to as offensive technology are vulnerabilities, exploits, rootkits, all these things, and they may go by somewhat different vocabulary in the jailbreaking and the kind of security communities. However, a lot of the technology is the same. The point is the same. It's getting increased access, maintaining persistence, and disabling security, bypassing and disabling security mechanisms, and so on. And so what we can do is we can take advantage of the fact that the jailbreak communities are observable. So it's one of the big challenges in defense is getting good observations of attacks and getting good data on it, because you don't know, for instance, how prevalent are Ios attacks in the wild. The problem is there's no antivirus on iOS. There's very few methods to determine that an iOS device is compromised. So, for example, we made a proof of concept called iVerify that is a deep boot ROM level, or it uses the jailbreak methods to boot an alternate RAM disk and do a deep verification of an iOS device. And this will detect any compromise and any differences. However, the vulnerability it takes advantage of is the same one that the jailbreakers use in the boot ROM of iOS devices that was fixed in the iPhone 4S and above. So for something like my iPhone 5, it's really hard to detect whether it's compromised or not, because there's no way that I can get that level of access to the device. So getting data or evidence of attacks in the wild for something like iOS is very difficult. So it's really hard for us to analyze what attackers are doing. So what we can observe are how the jailbreak community develops their tool chains and see which pieces of those can carry over to what would be used in a malicious attack, and observe them. And then we just have to be very careful of drawing only the conclusions that make sense from what we're observing from the jailbreak community, and not getting led astray. So let's look a little bit at the difference between jailbreaks versus attacks. So again, I said there's a difference in vocabulary. What the jailbreakers are starting to call injection vectors are roughly analogous to kind of a remote exploit. This is what gets initial access to the device to modify the file system. And what they call an untether is how they maintain a persistent jailbreak on the device. And so in the security community, we call that a rootkit. The whole point of doing the jailbreaks are to allow operating system mods, third-party, unauthorized or unsanctioned third-party apps, and just kind of a vibrant kind of homebrew community. Whereas attackers, they want to modify the operating system as well, but it's usually to hide their own actions, steal your data, and whatever. Jailbreaks are typically user visible. Attacks, do their best to be invisible. The jailbreaks are released into the open and can very often have open source components. The attacks can be released, the exploits, full open source, all their tool chain to generate return-oriented payloads and programs, all done. Whereas attacks, all you get is what you find on your system. The guys who develop jailbreaks they release these jailbreaks to legions of fans. They have press releases. They have donation accounts. They have tons of like parades in the streets whenever they release a new jailbreak. Whereas attackers, they're a little less egocentric, maybe, to the right adjective is. They try and release their attacks as quietly as possible onto your system. They're not going to issue a press release and be like, oh, by the way, none of you detected it, but we got a botnet on 10 million PCs in all these organizations. So some differences, but at their base levels, the technologies are the same. And this also leads to sort of what I consider my advice to vendors who are developing platforms like this. That by having a closed platform like iOS that is also popular, this creates a desire to be jailbroken, and that's actually created this very vibrant jailbreaking community that have developed pretty advanced offensive technologies to do this. And given any sufficiently popular consumer platform, there will be a jailbreak community to do this. And so unfortunately, some of these jailbreakers' public tools and like a lot of their research can also be instantly reused by attackers. So one example I'll go into a little later is the Jailbreakme jailbreak for iOS, which was essentially a remote drive-by-rootkit installation. And that's all I have to do as an attacker is, spider the website, download some things, replace the payload, and then send an email to all your friends who are using iPhones, and you have full access to their device. We don't, as a platform vendor, most likely do not want these ready-made attacks to happen on their platform. So you can take the fact that a jailbreaker and attacker's incentives and motivations differ, and you can kind of try and channel the jailbreaking efforts into areas that will and methods that will cannot be leveraged by remote attackers. So, for instance, if a jailbreak requires USB access to the device, it's less likely to be used by a malicious attacker as well as it just requires going to a website or reading a file. If that USB access requires the passcode because it uses a backup interface, it requires the device to be unlocked, it's also less likely to be used by an attacker because a owner of a device is going to know their passcode, and for them, running the jailbreak by typing in their passcode is not really a deal breaker at all. So what vendors should do in how they embrace the jailbreaking community is, I wouldn't say embrace, but how they deal with the jailbreaking communities for their platforms is attempt to shape their platform and how they respond in a way that minimizes the reusability of the jailbreaker's research for malicious attacks. So I'm going to tell you about how I'm analyzing these attacks. In almost all of my presentations over the last few years, I've used attack graphs. And if you're not familiar with them, I'm going to go a little over how at least I do them. I'll admit that I used to make fun of these because back when I started getting started in security in the mid-90s, I thought attack graphs were silly because it was like, I have a remote sendmail root exploit. So I go from here to remote root on your mail server and have everything. I mean, I don't really need a graph to show which path I take. It's just there. I have it all. And then there's remote roots against every Unix, system of the planet through RPC servers. I'm done. However, as we get more complex on the application stack, we have multi-sandboxed browsers like Chrome. We have the multiple security mechanisms like that exist in iOS, and a bunch of mitigations. Attack graphs start to make more sense because we're looking at the different choices that an attacker can make in going from here to there. So what we're going to do is I'm going to look at all the released jailbreaks and kind of draw out the level of access they start with, the level of access they end with, and kind of the intermediate capabilities they need to develop to get there. And going from one capability to the next, there's several different possible attacks that they can take, or several primitives that they'll need to combine. And I'll draw those differently. So, and we can also look at, if we sketch out kind of the security of a system in this attack graph and kind of brainstorm possible attacks, and then we overlay what the path that attackers actually took. The path that they actually took is a data point on what the least cost path from the beginning to the end is. It's not necessarily the least cost path because it's influenced by their experience, their preference, as just technical preferences. But it does give you an idea of what one of the easiest ways through there was. And one example of why it's not the least cost path is, for instance, the jailbreak community tends to do a lot more low-level binary exploits and never really do anything with web browsers. Whereas you look at a lot of the attacks on the internet and you have more browser attacks. But even though those would work against a lot of like Android and a lot of mobile platforms, jailbreaks and rooting exploits usually go more low-level. That's just because of the preference of the developers doing them. So the way I draw these is the square box has a level of access required or a capability. The borderless boxes like this is an action. So that's a vulnerability or an exploit or some sort of step that needs to be taken to get to the next level of access or capability. And let's kind of show the... next slide. Okay. My computer really likes this slide. All right, I'll click there. Keyboard does not seem to want to do anything anymore. All right, so this is the overall attack graph for jailbreaking. And this actually has changed a little bit because the most recent jailbreak that I'll talk about a little bit, it's called Evasion, kind of changed this up a little bit. But say we start with our device. We have physical access to it because we want to jailbreak our own device. We have it sitting in our hand. There's a few things that we can do to start getting access to the device. So some of the early exploits were in the boot process. So these are hardware in the boot ROM or the low-level bootloaders, and this would disable the iOS chain of trust early on, and then let the jailbreakers run or disable the security mechanism so they could keep access to the device and disable jailbreaking in the kernel after it booted. And because iOS has a chain of trust where the boot ROM verifies the integrity of the next stage bootloader, verifies the integrity of the kernel verifies the integrity of every executable, disabling the security mechanism in the bootloader basically lets you turn all that off. So that's our first alternative. The next one is we can exploit a user mode vulnerability that's accessible over USB. So after the device boots, there are several protocols that are implemented over USB and more attack surfaces that are available. But it's once the device is booted, so there's more security running at the time. Finally, our third alternative is exploit a user mode vulnerability through malicious data. So this is what can be done through the web browser or through a malicious PDF file, things like that. So I guess it's easier to point. Once we're in user mode and booted, code signing is active. So most access we're going to get is return-oriented execution. That's going to give us a limited amount of control, but not full code execution. So it's going to be a little difficult to implement our next stage attack. And typically what you want to do from there is exploit the kernel, and then once you have code running in the kernel, you can disable all the security mechanisms. If you've exploited a USB boot vulnerability and modified the kernel at boot time, you already have kernel code execution, and you can just turn off the security mechanisms. But at the end of the day, what that gets you is what I call a jailbroken kernel. That's just the iOS kernel without any of the security mechanisms running. And from there, you can either attempt to modify the bootloader, so this happens every time, or you need to get a kickstart to launch a kernel exploit at boot. So, because one of the differences with iOS versus other platforms is once you have full access to the kernel, you don't have guaranteed persistence from there. You have a lockdown bootloader, lockdown OS, So you're going to need to re-attack the system every time. And that's what's called an untether. Again, the keyboard decides not to work. So we'll kind of explode out this graph for the userland injection component, which is just getting to a temporary jailbreak. So if we're doing this all memory corruption style, we've got a pretty impressive path we have to go through. A number of vulnerabilities need to be chained, a number of mitigations need to be bypassed. So we'll start with like malicious data in the upper left. And we'll consider this like a PDF vulnerability, something that causes some level of memory corruption. So the first thing we're going to try and get is an information disclosure vulnerability. Because now that iOS has ASLR, we're going to need to reveal memory address, layout information, and in order to enable our attack. So once we have that, we'll have an ASLR bypass. But we don't have code execution yet, so we'll need to have another vulnerability, possibly the same, to exploit memory corruption, and that will get us some level of control. This is return-oriented execution. Because of what's called dynamic code signing, we can't just run shellcode. We can't inject new code into a process and have it run. iOS just won't allow that. So you need to reuse the existing code in the process and kind of piece that together to form your attack. So it's Turing complete, technically the same amount of power that you have with injecting shellcode, but it's a lot more laborious. So it's like writing a ransom note using letters you cut out from the newspaper. You can write anything you want, but just writing it out by hand or on a keyboard is much faster. So once we have that, we can alternately bypass code signing enforcement, and we'll still be in the sandbox, but we'll have basically shellcode running, just direct payload running. But then we'll need to escape the sandbox, and we'll still only be the unprivileged user. We might be able to find another privilege escalation vulnerability, and then we're running code as root. But on iOS, one of the other unique things is that the kernel is protected against the root user. They have what's called a secure kernel. So once you have root access, you need to still hack into the kernel. You can't just load a driver. You can't just do anything else. So you need to exploit a kernel vulnerability. Well, if you, at the end of the day, you have to exploit a kernel vulnerability, you may as well just do it the first chance you get. So once you have return-oriented execution, you can say, all right, if I can exploit this kernel vulnerability from ROP, let's just do that. However, if you need to get root first to trigger that kernel vulnerability, you'll need to get here before you go there. But the least cost path is just starting right there. We have kernel mode code execution. Disable security mechanisms is pretty easy. You're just patching things in memory, and then you're jailbroken. But that's only until the user reboots their device. If we want to persist, we have to do what's called an untether. So there's a couple ways to go about this. The first one is we can exploit an incomplete code signing vulnerability, which will, we'll assume that we start with privileged file write access. We got full privileged access to the device at some point in the past, and this is going to let us write whatever we want to the file system. So from there, we need to figure out a way to get something to happen at boot, because the device is still pretty locked down, and there's no shell. We can't just write a shell script in the boot process. You need what's been called a Kickstarter. So a Kickstarter is either a configuration file vulnerability that'll get code execution, or another trick that'll get something to happen at boot time. Once we do that, we get a binary to run. We still have code signing enabled. So we're going to need an incomplete code signing vulnerability in order to get one of those binaries to do something interesting. So that might get us return right to execution again, and then we kind of go through this whole process of exploiting the kernel. So what this gets us is boot time return right execution. We have to exploit the kernel again, and we can jailbreak. If we can kind of take that path where we drop a file in the file system, and at boot time it exploits the kernel, we have an untethered jailbreak. The alternative is by breaking into the Apple compound or rubber hose cryptography, we somehow obtain Apple's private key for their software, and then if we have that, we can drop a new signed kernel onto the file system. Even though I don't really think that, well, I can assume that both of those are pretty hard. I've been to the Apple campus and I've seen some of the areas with like these serious steel vault doors. I don't think that's where they actually keep the keys, but we'll just assume that's pretty hard. So, and I don't really have it in me to like beat up some engineer to try and get the key out of them.
I'll do it.
All right, she'll do it. Do you have a question?
Yeah, you're kind of verbally doing this, but if you like mapped out level of difficulty for each kernel, like where the drop off rates are.
So the difficulty of doing that is to gauge the question is, have I mapped out how difficult each of these steps are? To do that, you have to do them. So, how hard? Like, if no one's ever climbed a mountain before, how hard is it? How hard do you think it is? If you estimate how hard is it to climb that mountain, you'd be like, well, it's kind of taller than, I don't know, these other ones. It's very subjective. So the kind of analysis methodology is we look at how many people comprise the team. So some of these jailbreaks are developed by single individuals. And I use the word individual because I don't want to refer to Comex as a person, because he is elevated he's more of a status above everyone else. So there's mortals, and there's that range of skills. Comex exists floating above them. And he develops jailbreaks all by himself, but most of the other jailbreaks are teams of 4 to 6 people. So if you think about the amount of resources required to develop a jailbreak chain that were fully compromised an iOS device, it's a roughly full-time team of 4 to 6 people, 3 to 6 months of time. Compare that to an Android device. And those are usually compromised by, a single Rosenberg in a single afternoon. It gives you an estimate of the level of difficulty by just the observables. So that'll get you persistence on the device. There's been a couple different types of iOS jailbreaks, a couple different phases of how they've been developed, and I kind of separate them into different eras of jailbreaking. The first was a boot injection plus a userland untether, just boot injection and untether, where the best vulnerabilities would give you full access to the device and persistence, often through a single vulnerability. And the benefit here is that it's in the boot ROM, so Apple cannot patch it. All they can do is fix it in new devices. So this is the gold of jailbreaks, because they give you everything that you want forever, essentially, or as close as forever as you're going to get. However, once those were eliminated, jailbreakers had to start working harder. So now you can have a boot injection vulnerability that only lets you inject but not actually untether, and you need a userland untether. And the userland untether is where you need to go through the multi-step process of finding a kickstart, a code signing vulnerability, and a kernel exploit. And one or more kernel vulnerabilities in order to disable the security mechanisms. And I'll talk a little bit about how some of those worked. The third era was fully userland jailbreaks. These are userland injections, sometimes remote, sometimes over USB, and userland untethers. And these are the ones that get more complicated. I'll talk about, in particular, 3 jailbreaks that Comex did, and I won't talk about the absence jailbreaks, because there's those take 7 vulnerabilities, and I can't find a way to make the attack graph fit on one slide. But the basic point is, keeps getting to more and more work as you get closer to here. Started out being, a lot of the kind of the exploity stuff being done by 1 to 2 people, and then now it's to teams of, roving gangs of jailbreakers roaming Kuala Lumpur for Hack in the Box. So the boot ROM jailbreaks, the reason they're awesome is because they cannot be patched. They can only be fixed on a new platform, so they're forever against the affected devices. And an example of this was Pwnage 2.0, which is one of the best vulnerabilities that existed. This is a vanilla Stack Overflow in parsing the certificate in the boot ROM. So when you laid down the bootloader, it was signed, and it had an X519 certificate in it, and there was a Stack Overflow in parsing that. So the nice thing about this is it let you get initial access to the device and persist. Sorry, I just started getting sick 2 days ago, and I'm like, no, bad timing. So my voice might crap out in 2 minutes. But the way that the iPhone devices, or iOS devices boot, there's a thing called Dfu Mode, where you can upload a new firmware on the fly, and it'll execute. But it'll make sure that it's signed first. So this vulnerability existed there too. So you could upload a new firmware stage, and it would parse the certificate, it would exploit the overflow, and get code executing in the boot ROM context. Also, once you got initial access to the device, you could write a new bootloader onto the flash. So every time the device booted, it would the bootloader would open the next stage bootloader, parse certificate, boom, you got code running, and you're pretty good. So their attack graph looks relatively simple. We just start at the left with device access. We boot an unsigned RAM disk. There was actually the original pwnage had an easier to exploit vulnerability, which specified different boot args. You could boot an unsigned RAM disk without really any kind of binary mojo, and then have temporary access to the device. Once you had that, you could replace the bootloader because the bootloader was encrypted, not signed. And that was the first jailbreak. That was relatively simple. Pwnage 2.0 got a little more complex. We had to start doing actual exploit stuff here, like exploiting the Stack Overflow in the bootloader without a debugger and all this stuff. And so once you used the uploaded firmware to get initial access to the device, you just wrote that same payload onto the flash, and it would recompromise the device at each boot. The boot vulnerability that was used for the longest in newer devices was called limerain. And this was the first boot roll vulnerability that could not have been used as an untether. Well, there are some other ones, but they don't really matter as much. This was the big one that got used, couldn't be used as an untether. It was a heap overflow, exploitable over Dfu mode, but it only gave you temporary access to the device. You had to exploit it from a host computer with the right timing, with the right USB packets to actually trigger it, so you couldn't do that at boot. So in order, they'll give you temporary access to the device. You'd have to lay things down to the file system that would, start a new action at boot time and exploit the kernel. And so you'd interrupt the boot process, what's called a Kickstarter. There was one of many incomplete code signing vulnerabilities that would give initial return-oriented execution, which are chained into a kernel exploit. And this, before the release of limerain, there's actually an incident called the Shatter Incident, which is really illustrative of how the jailbreak communities can mimic attacker communities. So in order to get kind of the most PR fanfare, the chronic dev team who had been working on the Green Poison Jailbreak announced that they had a vulnerability called Shatter. And they announced the time they were going to release it at. October 10th, 2010 at 10:10:10. And they're like, everyone get ready, here goes. Right before that, so George Geohot was sitting on his own vulnerability he called limerain that he had for like 6 to 8 months. And so he saw that announcement, and he's like, oh, well, I'm going to release my own tool using my own boot ROM exploit called limerain, and I'm going to steal their thunder. I'm going to release it right before them. And what happened then is, I'm just reading this on Twitter, and because it's like an internal monologue. The chronic dev team had a moral quandary. They have a different vulnerability that their tool is based on. Should they release it and potentially burn that second vulnerability, or should they port their tool chain to use the now public vulnerability that Apple can't patch anyway, and potentially save that vulnerability that they have, keep it in their back pocket for the next device? Which is the right strategy, and that's what they did. But it was wishful thinking because Apple ended up fixing both of them in the next boot ROM. And perhaps Apple wouldn't have fixed it if they didn't know where to look, because the vulnerability name was called Shatter with a capital SHA. So I wonder where they started looking to see if there's a vulnerability there. So who knows? Or they could have found it anyway, but you never know. And this kind of was how the beginning of the transition into userland jailbreaks. So around the same time, Comic started releasing pure userland vulnerabilities because userland jailbreaks, because the boot ROM vulnerabilities are getting increasingly difficult to exploit or increasingly difficult to find, and there hasn't been one released since limerain. So for all we know, limerain was the last unicorn, and so all the jailbreaks are pure userland. So what happens now is there's a chain of low value vulnerabilities that are combined to form the jailbreak, and The problem here is that any one of those vulnerabilities being fixed breaks the entire jailbreak. So they're low value, they're fragile, they have low longevity. Once the jailbreak is released, Apple will typically kill most of them in the next patch, like the next iOS patch level. So, and as an example, Absence 2.0, that jailbreak used 7 vulnerabilities and 5 exploits. Any one of those patching would disable the entire jailbreak. So that shows just how much effort and how fragile that chain is. Just one link in the chain, it's all gone. So Comex's first jailbreak he called Spirit. And this one, your injection vector was over USB, had a directory traversal in the backup agent, the mobile backup. And that let him read and write files with privileged files onto the device. And that was his injection vector, fairly simple logic bug injection vector. But then his untether was the Kickstarter, kind of the triad, the Kickstarter, the code, incomplete code signing vulnerability to get initial execution, and then a kernel exploit. The kernel exploit he used was actually really interesting. This one required root access to exploits, so while present in other Unix-based operating systems like other BSDs, it wasn't a security vulnerability because to sniff the network, you needed root access anyway. However, on iOS, this root access memory corruption vulnerability gave you kernel execution, and that was actually a security bug. But as we'll see with a lot of Comex's jailbreaks, he has a particular style. This kernel vulnerability was in the Berkeley packet filter interpreter. So the Berkeley packet filter has a compiler that turns the text that you specify for like a packet filter, like if IP address does not equal this and port equals 23, compiles that to a bytecode, and the kernel interprets that bytecode. He went through that bytecode interpreter and found a memory corruption vulnerability, exploited that. So then I made a bet that something like this would never exist for iOS, and it turns out it did, not just once but twice. And so I was a little ashamed to admit that because I never thought someone would invest this much effort. But they did. So Jailbreakme 2.0, also done by Comex, was the web-based jailbreak for iOS 4.01 and below. And it also gave me an idea of how fast these are patched. So he spent stuff in here. So basically how it worked was he found a vulnerability in the car string parsing of the free type font rendering engine that iOS used. And what car strings are is they're a embedded interpreter for a bytecode language that allows the font to be rendered to the screen. And he found this vulnerability that would actually let him just corrupt memory and get return-oriented execution. So from there, he would exploit the kernel directly to another vulnerability called Ios surface, and he did this directly from return-oriented program. He didn't actually need to bypass code sign and go through all those extra steps. And then it temporarily jailbreaks the kernel so that you can write the injection vector or write the untether onto the disk, and then exploit the same vulnerability at boot each time. So I want to talk a little bit more about these car strings because they're somewhat interesting. They're an interpreted font program, and there's a small specialized stack-based virtual machine inside FreeType that interprets these. And the bug was that the depth of the car string stack was not validated, was not enforced. So if you pushed too many things onto the stack or did another sequence of operations, you would go out of bounds. So, and what that would do is that would exceed the car string stack and start corrupting the CPU stack that the thread is actually using. And here is the car string that this exploit actually used, which, as you can plainly see, what it does is it pushes a bunch of data onto the stack, because the way that a car string works is if it's I can't remember the encoding the integer. If it's just encoded as an integer, it just gets pushed onto the stack. Otherwise, it's an opcode. So all this stuff at the beginning is a bunch of data that gets pushed onto the car string stack, and then a sequence of operations are repeated in order to adjust the car string stack over the right place of the threads, the CPU's thread stack, and then it writes that data onto there, corrupting the actual CPU stack. And then when the function returns, it uses a crafted return address, does return-oriented programming, blah 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 blah. So it's all really complex, but it's not just this simple. The point is, it's not the simple long string make things go bad. It's these sequence of steps make things go bad. And the vulnerability that it exploited was a vulnerability in the kernel driver called Ios surface. And there's an integer overflow here that when you pass like an XML plist to the kernel saying, hey, I need an IO surface, the integer, like the allocation size would wrap, and you would actually get a memory buffer that referred to kernel memory. And so the return to program in userland could bounce around and start adjusting kernel memory from userland, which is pretty cool. And so how it works is just two large integers, chosen for a specific value to cause a integer allocation over to wrap around and return kernel memory. So the untether, how that works, so it first starts the Kickstarter, which is if the file launchd use gmalloc existed, launchd would use a debug, try to load up a debug library. And so what Comex could do is line that library onto the disk, hit that flag file, and then when launchd ran, it would load up his dylib. But because code citing was still enforced, and as far as I know, he didn't beat up some poor Apple guy to get their key. He needed to get by code signing. So this libgmalloc.dylib has no executable segments, so no code needs to be signed. But what it allowed is it specified other things, a feature called DYLD interposition, to interpose on certain shared library functions. So when those were called, when they were called by launchd, instead of calling a real function, they would jump somewhere else inside launchd, do what's called a stack pivot, and so move the stack pointer into attacker-controlled data and start doing return-oriented execution. And then use ROP, exploit a kernel bug. So, fairly sophisticated chain of stuff. So after all this was fixed, fast forward about a year. Yeah, I think it was a year because it was also in the summer. This was a jailbreak called Saffron, which was largely a deja vu of Star, which was interesting because each component was roughly analogous to the component it replaced. Again, there was a malicious PDF file with a crafted font that would get code execution and do the exploit. But instead of being a CFF font with a malicious car string, this is a type 1 font, and there's a type 1 font program that does another embedded virtual machine inside a font file that would exploit this bug. And then that ROP payload would exploit another kernel vulnerability through IOKit. However, the challenge this time was that iOS at this point had ASLR, so the exploits had to be a little more sophisticated. But again, after the date that Comex released it, exactly 10 days later, Apple patched it. So, again, a very short lifetime. But how this worked here is type 1 font program it's interpreted, has programmatic access to ROM memory. So it does what's been called kind of the weird machine style of exploitation. And what it's able to do is using this font program to build primitives that can read a pointer value from elsewhere in memory, compute what the slide is, which will basically figure out how much it's been moved by ASLR, and then it dynamically adjusts the return-oriented program for that slide, copies it onto the stack, and then executes it. This is, this exploit is, self-aware. It's getting a little scary. From there, again, exploit the kernel, using ROP and do all the same stuff. But I want to talk a little more about this car string or this free type vulnerability. So what this one is that there's a byte code called call other subroutine, and the argument count to it can be negative, and that'll move the interpreter stack out of bounds. And now every operation that affects the interpreter stack is now affecting memory out of bounds on the CPU stack. And bad stuff can happen because there's a state structure that's written onto the stack called T1 decoder rec, and that's basically the state of the interpreter. And now the interpreter, the interpreted font program has direct access to the state that controls how it's being controlled. And this font program, what some people call a weird machine, basically builds kind of these primitives out of the weird access it has to gain increased access to memory. So in the font program, it's really hard to read on here, but once we get to this instruction here, this call other subroutine kind of bytecode specifies a number of arguments, negative 3047, that'll shift the stack elsewhere. And then so all this stuff right here that follows are chosen not for their functionality, but for how they'll affect the how they'll affect the stack and how they'll write to the stack. And there's actually a really good blog post that explains this, explains how this font exploit works. I'd recommend setting aside at least a weekend to try and read through it and understand it because it's a bit complex. But again, Comics uses the same uses the same Kickstarter with loading libgmalloc because Apple didn't fix that in the last time around. They didn't consider it an actual vulnerability. This time he used Mako relocations as his code signing bypass, his incomplete code signing vulnerability, and basically used that to adjust the ROP and do all that stuff. Again, exploits the kernel. So one of the trends over the kind of, I guess with a lot of Comics' vulnerabilities, is these like font-based ones had to combine what most people are calling exploit primitives now. So a long time ago, a single exploit would give you enough power to get code execution. A vanilla Stack Overflow, you overwrite the return address, jump into your memory, that's really all you need. However, what's increasingly common is that because of exploit mitigations and more specialized kind of one-off vulnerabilities, each security vulnerability or memory access or memory corruption vulnerability only gives you a slight amount of power, increased capability. And so you combine these in order to finally build up to code execution. So these are called, what people are calling these exploit primitives. If you look at the evasion jailbreak, this one especially demonstrates how these are combined. And their kernel exploit has to combine several of them, but also their injection vector combines 3 different logic bug capabilities in order to write to the file system. If you compare this to the Star jailbreak that Comics first released, he had just one vulnerability that would let him write anywhere to the file system. So he didn't really need these primitives, but this is where we're at now. And so basically, I'll kind of go a little bit through this graph here. What we have now is we have 3 separate stages to the jailbreaking process, which should be familiar by now. So once we have physical access to an unlocked device, so that's what's so unique about this jailbreak. It has to be unlocked. We're going to inject our untethered payload onto the file system. So what we want to get from this is boot time privileged command execution. And this is done through 3 separate vulnerabilities that are not chained because they're not like they're giving increased stacks, like increased privileges, but I think of them as being combined in order, like as primitives to get the next level of access. So for instance, the first one, the basically file relay service, would let you only read files outside of the normal like backup domains. So that's one useful primitive. But and they would use that to read the app cache, so they can actually rewrite the app cache and install a new app. But to write it, they needed a second vulnerability, and that was a kind of directory traversal / symlink attack through mobile backup. So that let them plant files on the file system. And now with that, they could actually install a new app. When that app is clicked, it'll run a few commands using kind of a few other tricks that I don't really consider vulnerabilities. However, that's not enough to get root on the device. In order to get root, they needed a third vulnerability, which was the lockdown time zone chmod 777 vulnerability. What that was is that the lockdown daemon would always make the time zone file readable, writable, and executable by everyone. But it would follow symlinks. So, because we had this symlink attack in mobile backup, they could use that to make any file readable and writable by all users. And so what they use that to do is to make a socket that launchd talks to, or launchctl talks to launchd over, writable by everyone, which effectively gives them root. Because now that was the mechanism that prevented normal users from submitting commands to be run as root. They'd be root anyway to talk to that socket. But now that you could talk to that socket, you could submit commands to be run by launchd as root. So if you combine those three primitives in a blender, what you end up getting is privileged command execution out of it. I can now run commands as root on the device. The next step is I remount the file system as being writable, and then I plant a file in the file system, launchd.conf, that'll get loaded and executed at boot, and from there, from launchd.conf, I can specify launchd bs or launchctl bs exec commands to basically run commands as root. So now I have persistent privileged command execution at boot. That's one stage that required multiple primitives to be combined. The next stage of the jailbreak is disabling code signing. This required just two primitives. One is a kind of an overlapped segment problem that allowed them to craft a binary that would basically allow them to interpose on functions again by having kind of some of the headers in the file overlapping themselves. So with that, and being able to execute commands the way they could load up a shared library into this background daemon called AMFID. AMFID is the daemon that basically tells the kernel whether the signature for a given binary is okay or not. So in that binary, they're able to interpose on this function that's basically, is the signature okay or not? And so make it just patch it out to always return true. And so now whenever the kernel would ask this userland daemon, is the code signature for this binary okay? It always says yes. And so by combining those two primitives, they have arbitrary code execution, which will let them run their exploit at boot. And then once they have that, they have a fairly complex kernel exploit that required two initial vulnerabilities. One vulnerability that would leak a kernel address of data. So what they could use that to do is to allocate a bunch of buffers and then put some crafted data at a known location. And they combine that with a second vulnerability that would allow them to treat a chosen address as an object in the kernel. And they could turn that into calling any address as a function. And that was their call and direct anywhere primitive. And the create data was the use kernel known address primitive. With both of those, they combine them in other interesting ways for a read anywhere and a write anywhere primitive. There's another I'm not really sure if I'd call it a vulnerability, but Apple fixed it, kind of like an information leakage thing that would help them read data. But basically, using all these tricks, kind of overlaying some capabilities from one vulnerability to another, they were able to actually finally build to full kernel mode code execution. And this was I think this is like a 5,000 line exploit, which is, for kernel exploits, that's a little up there. And then with all these, boom, you get the jailbreak. But the trend here is that, you're starting to see the single vulnerabilities are not getting you from one level of access to the next anymore. The level of access they're getting you is a little bit of memory read, a little bit of memory write. We have to combine them in creative ways to actually get code execution. And what this is showing us is that as Apple eliminated the boot ROM vulnerabilities, that pushed the iOS jailbreak community to look for these userland and web-based jailbreaks. And these are the types that actually could be leveraged by remote attackers. So the existence of these are worse for Apple iOS users. And what this caused is that some of these jailbreaks provided all the exploits needed for drive-by rootkitting of iOS devices. And a colleague, another co-founder, Dan Guido, did a presentation called Mobile EIP that showed when he analyzed all the mobile malware he could get his hands on, it showed that the malware authors never developed a single privilege escalation themselves. They would always borrow one from the community. And these are all Android apps, because couldn't find any malicious iOS apps that actually escalated privileges. And they're taken from the Android rooting community. So the existence of these rooting exploits and these jailbreaks has made the attackers' jobs easier. But we can make sure that the jailbreaks do not help these attackers in several ways. So for instance, the kernel vulnerabilities often used by iOS untethers will require root privileges. Since no app runs as root, these are going to be useless in a malicious app. A malicious app is not going to be able to use these to gain privileges on your device. The only ones that are useful are ones that run as an unprivileged user. And one researcher, Dan Rosenberg, for instance, he made a point not to release any Android privilege escalations that could be used within an app. All of them, if they could be used within an app, he wouldn't release it because he considered it too dangerous. So this is what I would call responsible, rooting tool disclosure. And what this shows is that if vendors should patch the app privilege escalations instantly, because malicious apps bad for everybody. But untether vulnerabilities that require root access already to use are not really that dangerous because they're just going to be used for jailbreaks. So there's no actual reason to patch them, because if you do, jailbreakers will develop something else that might require, that might also be, it might be leveraged by an actual attacker. Whereas if you leave them that vector, they'll just keep using that, and it won't put users at risk. In an ideal world, here are the things that I'd love to see. I want to see a developer mode on all devices that disables secure boot and allows execution of homebrew software, so you can do all the cool stuff that you want to do. But I want to make sure that there's a visible indicator on my device that it's in this mode at all times. So, like when I come back to when I leave my phone, around someone at work, and I come back, I want to make sure that it, knows that, or I know that it's been switched into this mode. Or alternatively, when you switch into developer mode, it wipes the device automatically, so that I know that it's been wiped. And this will discourage the creation of jailbreaks using vulnerabilities and exploits, because you just do it using that built-in mechanism. There's no reason to develop this offensive technology that could potentially be of use to attackers. And then attackers cannot piggyback on the work of jailbreak development teams. So that's my thesis. Anyone have any questions? Yeah. Right. I mean, it's hard to really measure the attacker interest in those devices, when there's no real attack data. They're essentially jailbroken. They're essentially vulnerable for life because they're not supported anymore. There's publicly accessible toolkits to own them. So for people wanting to do hobbyist stuff, they can always get those old devices, but people want to jailbreak the device they have already, and they want to up, the flashier one. So I haven't really seen anyone say hey, I really want this. I'm buying up all the old iPad 1s on eBay so I can do cool stuff. Maybe artists and hackerspace kind of people, but I don't know. Yeah.
Sorry. It kind of sounds like you're describing the evolution of potentially drugs. And I was wondering if you have any thoughts on how developers or vendors could use that kind of energy towards. People are going to work on this anyway. Is there any way to kind of jujitsu that energy towards something more useful for the actual vendor?
That is a more advanced maneuver than what I've been able to think of so far. I've been thinking about how to jujitsu that to something that's not dangerous for the platform, like not helping attackers, but I actually like your metaphor of antibiotic-resistant drugs. Not sure what you could jujitsu them into doing, like mowing your lawn. That's a very hyper-advanced maneuver, because mowing the lawn is much less fun than writing jailbreaks. So I know which one I'd rather do. And I'll give you a hint. I live in New York City for a reason. Any other questions? All right, cool. Thank you very much. Sorry for the voice.